All right, today we're diving into a paper that puts forward a pretty wild and maybe even fundamental idea about deep learning. It's called the universal weight subspace hypothesis. So let's get right into what it's claiming. So what is this hypothesis exactly? Well, the core idea is actually pretty straightforward, but its implications are huge. It suggests that deep neural networks, it doesn't matter how you initialize them, what task you're training them for, or even what kind of data they're seeing. They don't just wander off and find their own unique solutions in that massive high-dimensional parameter space. No, instead, they seem to systematically funnel down into the same shared and surprisingly low-dimensional areas. It's like all roads lead to the same small neighborhood. And this plot right here, it's a fantastic visual for what we're talking about. What you're seeing is the spectral decay for a whole bunch of different models, GPT-2, Vint, Llama, you name it. And look at that sharp, consistent drop-off. It's happening across every single architecture. What that tells us is that just a handful of principal directions are capturing almost all of the important information or variance in the model's weights. That black line, that's what you'd expect to see if every model was finding its own independent solution. But the data? The data tells a completely different and frankly much more interesting story.
Okay, so we've seen this strange pattern, but is it just a fluke, an interesting quirk of the models they tested? Well, no. The authors actually ground this whole thing in some serious math. Let's take a quick look at the theoretical underpinnings.
So, to make this rigorous, the authors framed the entire problem within a Hilbert space. Now, this gives them the right mathematical machinery to properly analyze these task predictors. The key object they focus on is the covariance or second moment operator of these predictors. This is what allows them to formally define and then analyze that common subspace that seems to be spanned by the solutions to all these different tasks. And this leads to a really crucial piece of the puzzle, Theorem 2.5. This isn't just hand-waving. This theorem provides actual convergence guarantees. It proves that the shared subspace we're seeing in the experiments isn't just some statistical accident from a limited set of models. It shows that as you pile on more tasks and more data, the subspace you learn empirically actually converges to a true, underlying universal subspace. This confirms that this shared structure isn't just an observation. It's a fundamentally recoverable property of these networks.
All right, so the theory is solid, but does it hold up in the real world? This is where the paper really shines, with a ton of large-scale empirical evidence. Let's dive into the experiments and see how this hypothesis fares under some serious stress testing. First up, they start with a classic, ResNet 50. They took 5 of these models and trained them completely from scratch on totally separate datasets. You'd think they'd learn completely different things, right? But when you analyze their weights together, you see this distinct shared low-rank structure. Just look at the plot. That's that same rapid spectral decay we saw before. A tiny number of principal components are explaining almost all the variance across all 5 independently trained models. Pretty wild.
But okay, that's just 5 models. Things get even more interesting when they scale this up. And the key to scaling it up was using parameter-efficient adapters, specifically LoRAs. Because you can train and collect these things by the hundreds, it lets the authors really put the hypothesis through its paces. And I mean really put it through its paces. Check this out. We are now looking at 500 unique LoRa adapters for Mistral-7B. Each one was fine-tuned on a different instruction following task. And the result? It's completely unambiguous. You see that exact same sharp spectral decay. This is incredible evidence. It means that even across a huge, diverse set of 500 different tasks, all the fine-tuning adjustments are happening within the same tight, low-dimensional subspace. And this right here is really the mic drop moment for the empirical evidence, because it's not just one model family or one type of data. We're seeing the exact same pattern, the same collapse into a universal subspace across hundreds of vision transformers, scores of Llama 8B models, GPT-2, FLAN T5, the list goes on. When you see something this consistent across such a wide range of architectures and modalities, it starts to look less like a coincidence and more like a fundamental property of how these networks actually learn. So we've established this phenomenon is real. It's backed by theory and a mountain of evidence. But so what? Why does this matter? Well, it turns out the existence of a universal subspace isn't just a cool academic finding. It has some really profound practical implications for how we can build, train, and even deploy our models. The benefits here are actually huge. Think about it. If all the solutions for different tasks live in this one small subspace, what can we do with that?
Well, for starters, massive model compression. Suddenly you don't need a whole new model for every task. We're also talking about super fast adaptation to new tasks, because now it's just a matter of finding the right coordinates in a space you've already mapped out. And it completely changes the game for things like multitask learning and model merging, giving us a new, much more principled way to approach them. And this plot really drives home those efficiency gains. Take a look. The models projected onto the universal subspace, those are the blue and red squares, they're getting performance that's right up there with the fully fine-tuned models. But here's the kicker. They're doing it with a tiny, tiny fraction of the parameters. This is a game changer for the whole performance versus efficiency trade-off. Let's get specific with model merging. Look at this table. You've got a few state-of-the-art methods here, like ties. They're okay, getting in the 60s, but the universal subspace approach, it hits 83.5% average accuracy. That is almost identical to the fully fine-tuned performance of 84.1%, and it just blows the other methods out of the water. Oh, and by the way, it does this analytically, no fiddling with hyperparameters. Just to really put a number on those compression benefits, get this. The authors showed that they could take 500 different vision transformer models and represent them essentially without loss inside a single universal subspace model. That's a 100x reduction in memory, 100 times. And what's crazy is that this efficiency actually gets better the more models you add. And this isn't just for classification or language tasks. The hypothesis holds up for generative models too. What we're seeing here are a bunch of stable diffusion LoRAs. Each one has its own unique artistic style. They were all projected down into one universal subspace. Now look at the comparison. The top row is the original individual LoRAs. The bottom row is generated from that single combined subspace model. It's uncanny how well it preserves each distinct visual style. The numbers back this up too. When they measured the average clip score, which is basically how well the image matches the text prompt, the universal subspace model actually scored a tiny bit higher than the individual LoRAs. That's a really interesting result. It suggests that projecting into this subspace might actually be cleaning up some noise and improving the model. Okay, so this is all incredibly compelling, but like any truly big discovery, the universal subspace hypothesis raises just as many questions as it answers. The authors are very upfront about this, pointing to some really interesting open questions and future directions. So what's next? Well, there are a few big unanswered questions. First, what are these principal directions? What do they actually mean? Figuring that out, the interpretability problem, is a huge challenge. Second, right now you need a bunch of trained models to even find the subspace. Is there a way to find it directly from the data without that first step? And finally, how does this whole idea connect with other concepts we've been exploring, like task arithmetic? Can we do math with tasks inside this subspace? And that brings us to the final and maybe most provocative question the paper leaves us with. If all of our best, most powerful models, regardless of their architecture, regardless of their training data, are all collapsing into the same small subspace, if they're all inheriting the same inductive biases, the same fundamental capabilities, then we have to ask ourselves, is this a feature or is it a bug? Could this lack of diversity actually be a fundamental bottleneck for artificial intelligence? It's a huge question and one that the field is going to be grappling with for a long time to come.